So the review session will be tomorrow at 5 p.m. So this is what, August 18th at 5 p.m. Eastern time. This will be recorded and will be made available to you for watching at a later time. But I think, so the winner of the poll was actually Wednesday 12 noon by one vote. But I think that Wednesday 12 noon is kind of too late, given that the exam is on Thursday. And I feel like most of you will get done with most of your classes by Tuesday 5 p.m. So I think Tuesday 5 p.m. is the best time to have this. So it lost by one vote, but I think that's the most appropriate choice. So that's when I'm scheduling the final exam review. I will send you guys a WebEx invitation to join on this link. I can tell you it's going to be in my WebEx personal room. So if you know how to join, then you don't have to wait for that. What says lecture 25? Is everybody seeing lecture 25, or are you seeing the final exam review session being written on it? Yeah. Final review, yes. Oh, okay. What would you like the name to be? All right. All right. So the review will be on Tuesday, and this is when I'm going to talk about exactly what you should focus on. So there are some key topics for the class. So while you prepare for the final exam that is comprehensive, I don't want you guys to lose track of what you really need to focus on. So because there is overwhelming amount of information that we have covered during this summer semester. So what I'm going to do is I'm going to give you guys specific targets, specific topics, and in fact specific things I'm going to test on in that particular topic, so that you can focus your time and energy in preparing and reviewing those specific ideas. That's the best I can do. Apart from, I'm not going, of course, I'm not going to go as far as just giving you the exam as well, but I'm stopping one step before that. So I hope that you will take this opportunity to really put in your best effort for the final exam and score high, because now you know what the questions are going to essentially look like. So for example, as I mentioned a few minutes early, there will be a continuous time convolution problem on the final exam, where I will test whether you can take two continuous time signals and convolve them using graphical convolution and give me the result, most likely in bracket notation. So that is one very key topic that we learned in this class, which is going to appear on the final exam. Now, I'm not going to tell you what signals, but that will be there. In the same manner, I will talk about the other questions. So for example, Fourier series, Fourier transform, those are key ideas for the course. So I'm going to give you some specific targets to aim at during the final exam review session. The final exam is going to have two time slots as usual. Exam 1, similar to exam 1 and exam 2. One time slot is going to be during the regular class time, and the other time slot is going to be on the same day, Thursday, August 20th, later on in the day. So 9 to 11 p.m. The exam itself will be for 2 hours, out of which you will use the last 20 minutes for scanning and uploading. So similar logistics as the previous two exams. So hopefully there is no confusion as to what to expect. I'm going to assume that all of you would like to take the final exam in the same time slot as you did for exam 2, which means the last exam that you took is the same time slot I'm going to assign you by default. But if you would like me to change that, please inform me by email before Tuesday, tomorrow, 11:59 p.m. Eastern. Now, how do I know which time slot I signed up for? Go to Gradescope and take a look at your exam 2 submission. If you submitted your exam 2 on Gradescope in the submission that was titled exam 2 time slot 2, then of course you were assigned to time slot 2. But if you submitted your exam to a submission called midterm exam 2, then you were time slot 1. So by just going to Gradescope and looking at where you submitted your exam to, that's how you know which time slot I am going to assume by default for each one of you. But you can change it if you need to. Please email me before the date mentioned on the slide. Questions here? Will there be a homework related with the materials that we learned today and last lecture? No, there will not be any homework that is due. But if you guys would like some practice problems, I'm happy to provide some practice problems. I've also uploaded several final exam back exams for you guys to practice. But no more homework due. Homework 19 is your last homework that is due tonight. So I didn't assign a homework on Thursday. I'm not assigning any homework today as well. Will this material be on the final exam? Some part of this will be on the final exam, and I will tell you what aspect of this material will be on the final in just a bit. No problem. So not all of it, because we are trying to cover Z transform, which is a very big topic. So I'm not going to hold you responsible for everything that we cover today, but the basic of it, finding the Z transform or the inverse Z transform of a function and the region of convergence. That is it. I'll talk more about that as we get into the lecture. Other questions? No, not all the properties. They will be available to you, but I'm not going to test that just because it is too close to the exam and not enough time to process. Okay, so it looks like the questions are slightly moving towards something else. So let's move into that direction, which is the next lecture, right? So lecture 21, with your permission, I think now I can change this, right? Lecture 21, I have many things that are on my mind, but depending on the time, we will get through as much as time allows. So my goal is Z transform properties. How does Z transform apply to discrete time LTI systems, stability, and solving difference equations? So lots of things, but we will get to whatever we get to in the given amount of time. Let's see. So what is the Z transform? What are we using this for? And let us do an example. So the Z transform is like the Laplace transform but for discrete time systems. So signals. So let's see if I can write this here. Think of this as Laplace for discrete time signals. Now, when we were learning Laplace, we saw that Laplace transform was a generalized form of Fourier transform. In other words, whenever the Fourier transform would not exist, we would borrow a factor and then evaluate the Laplace transform and then define the region of convergence for which that particular transform would converge. Right? And the same thing, a similar thing is what we are doing with the Z transform. So Z transform is a more generalized version for discrete Fourier transform. So even though we have not looked at discrete Fourier transform in this course, we are going to apply a Z transform to find two things, right? So essentially Laplace transform gives you what? It gives you two aspects of systems. One is the frequency response, right? So S has sigma and j omega. J omega is what relates to the frequency. So that's how we find out the frequency response of a system. And the other is the stability, right? So we would know by observing the Laplace transform, is the system stable, unstable, is the system stable, marginally stable, or unstable? We would know that. So stability and frequency response, those are the two key outcomes of Laplace transform. And the same applies for Z transform as well. One thing is we would know the frequency information, but in discrete domain. The other is the stability of discrete time systems. So those are the two things that we are after with Z transform. Two main things. Now, how do I find a discrete, the Z transform for a discrete time signal? So x of n is a discrete sequence, right? N is the sample number, right? So if you have a sequence of numbers denoted in this discrete time signal x of n, I can find the Z transform of this x of n by applying this summation. X of z, cap x of z, that's a two-sided Z transform of x of n. X of n is a discrete sequence. So summation of n from negative infinity to infinity, x of n multiplied by z to the negative n, where z belongs to the set of complex numbers. The same way S was belonging to a set of complex numbers. S had sigma plus j omega, where sigma was the real part of S and j omega was the imaginary part of S. Now we are using z to describe discrete frequency, where z belongs to a set of complex numbers, r is the magnitude of z, and cap omega is the angle of z. So another complex number like S, but now we are denoting that in polar form. And there is a reason for that. The reason is a rectangular coordinate system suits very well for sigma and j omega in the S plane. But a polar coordinate system suits well for the Z transform. And when we start talking about region of convergence, you will see that like we had the region of convergence going to the right of the rightmost pole and to the left of the leftmost pole, or it was a vertical strip, or it was no space at all. Now with the Z transform, it is going to be very similar, but it is going to be with respect to circles. Outside of a circle, inside of a circle, a ring, or none at all, right? So because of that circular nature, polar coordinate system suits very well for Z transform. That's why we are expressing Z as r e to the j omega. Omega is the angle of that complex number and r is the magnitude of that complex number. The notation is very similar to what we have been seeing so far in the course. Left hand side is your time, right hand side is your z. X of n, when you take the Z transform, you get cap x of z. Now let's do a very simple example. X of n is defined as a sequence of elements, and clearly there is a underline there, which means this corresponds to time 0. That is when n is 0. And over here n is -1, over here negative n is 2, over here n is 1, 2, 3, and so on, right? So how can I find the z transform of this? Well, I'll simply plug this x of n into this summation, two-sided summation, to find that out. So I can clearly say cap x of z is going to equal, the first element that I'm going to get is for this -1, right? So I'm going to get -1 multiplied by z raised to 2, because at that time n is -2. So z raised to negative of -2 will become z raised to 2. Next, I have -1 for the next element. Sorry, not -1. It is 2 is the value at -1 plus 2 z raised to 1. And then I will have the third value is 3 z raised to 0 plus 1 z raised to -1 plus 1 z raised to -2 plus zeros. Everything else is 0, right? So you have got a function is z, that's your x of z, but where does it converge, right? ROC. Now clearly, because of this and this, I do not want z to be a 0, and because of z squared and z to the 1, I don't want it to be, let me shade this in something else, maybe blue. Because of this and because of this, I don't want it to be infinity either, right? So ROC in this case is going to be set of all complex numbers, but I'm going to have to remove 0 from it because of the yellow highlights, and plus and minus infinity from it because of the blue highlights. Because there is a z inverse there and there is a negative power of z, so I don't want z to be 0, and I also don't want z to be infinity. That's when x of z will not converge. So the region of convergence is everything in the complex z plane without 0 and plus and minus infinity. So that would be the region of convergence. Next, so that's how you would essentially take a timed sequence and find its z transform. Just plug and play, find the region of convergence based on whether it is converging, whether it is going to infinity for some values of z. Now let's take another example here. X of n, your discrete time signal, is defined as 2 raised to n for values of n between 0 and 10. So this is a finite duration discrete time signal. It starts at 0, ends at n equals 10. And at every other place, it is going to be 0, right? Now, if you sketch this out, you can clearly see this. If you sketch this 2 raised to n, what are you going to have? This is n. This is, say, x of n. What are you going to have? At 0, you are going to have 1. And you will have 2, and you will have 4, and then it will go on to what? 1, 0, 2, 4, right? So it's going to exponentially increase. Maybe not the best approximation here, but it is going to exponentially increase. But because it is a finite duration discrete time signal, it is going to converge. So because we are adding a limited finite number of elements. So let's see, I can write, based on this, I can write x of z the same way as I did in the previous example. Multiply each value with decreasing powers of z, starting from, in this case, z equals 0. So you would get 2 raised to 0 multiplied by z raised to 0 plus 2 raised to 1 multiplied by z raised to -1 plus 2 raised to 2 multiplied by z raised to -2, and so on. up to the last element. Everything else is going to be 0. Now that is a sum of finite geometric series, because in every term I am multiplying with 2z raised to negative 1, right? That's every time is every element in this geometric series is getting multiplied by 2 raised to z to the negative 1. And I get the next element, and I get the next element. So I can apply the sum of finite geometric series formula to find out this particular sum. And I have the formula on the next couple of slides, but if I apply that, I will get 2 raised to 11 z raised to negative 11 minus 1 divided by 2 raised to z to the negative 1 minus 1, which I can multiply and divide by z raised to 11 to get into this form, right? So I'll just write that in blue. Multiply and divide by z raised to plus 11 to write it in this form. Now for this, the region of convergence is going to be set of all complex numbers, but because you have negative power of z, negative power of z, negative power of z here, you are going to have a 0 that you need to exclude from the region of convergence. Everywhere else it is going to be converging. Next, just as a reference, we need the sum of geometric series formula. The first one here is for a finite series, and on the next slide I have one for an infinite geometric series. So if you have a series over here that you are adding up 1 plus r squared and so on up to r raised to cap n, so n, cap n is a finite number. So essentially you can write that in compact form using the summation small n going from 0 to cap n, r raised to n. That equals r raised to n plus 1 minus 1 divided by r minus 1. So that's the formula that we used in the previous example. Now if x of n has finite duration, like we did in the previous example, it means that it has finitely many pulses. It had how many? 11 pulses in the previous example, 0 to 10. So 11 in total. Then the sum in the z transform will always converge. So that means that z belongs to a set of all complex numbers will be converged. It will be valid. However, because I may sometimes have negative powers of z, I need to exclude 0. And for all the cases where I have positive powers of z, I need to exclude plus and minus infinity. So I can actually use this over here. But it will converge because it's finite duration. So if your coefficient, if your values in the signal are finite and it is for a finite duration, then you will have the z transform converge for everything in the z plane except for 0 or plus and minus infinity. That determination needs to be made after you actually look at the z function in z. So if you see negative powers of z, then you need to exclude 0 from the region of convergence. If you see positive powers of z, then you need to exclude plus and minus infinity. Now, if the series is infinite series, like the one that is shown over here, 1 plus r squared plus and so on to infinity, it can be written up in a compact manner using this summation n equals 0 to infinity r raised to n, which simply boils down to 1 divided by 1 minus r. This only happens if the magnitude of r is less than 1. But if the magnitude of r is equal to 1 or greater than 1, then this summation will diverge, right? So if say r is half, what do you get? If r is half, you get 1 plus half plus 1/4 plus and so on to infinity, which will essentially get you 2, approximately 2, right? But if you have something like 1 plus 2 plus 4 plus so on, this will be infinity. That's not going to converge. So this is where r is half and this is when r is 2. So only when every time you are multiplying by a factor that is less than 1, only then it will converge. Otherwise it diverges. Now if x of n has infinite length, the summation becomes infinite sum. It might not converge for some values of z. So for example over here, when r was 2 or any value greater than or equal to 1, that summation would not converge. The only way to make it converge is to make the magnitude of r less than 1. So we are going to borrow this to find the region of convergence. We are going to use this to find the region of convergence for some of the Z transforms. Let's take a look at the Z transform of our favorite signal, the unit step. This is your, step sequence in discrete sign, right? X of n is U of n. It is a right-sided signal, right? So why is it right-sided? Because in time it looks like this. This is n, this is x of n. So how does it look like? It has 1 here, 1 here, 1 here, 1 here, and so on, right? Everything else is 0. So it's a right-sided sequence. And now we are trying to find out the Z transform of x of n. Using the Z transform formula. And right now we are like taking for granted that this is the formula for the Z transform. But a little bit later in the lecture, we will see where this formula actually comes from. It comes from the same idea that we used in Laplace. When you give an LTI system an input of a complex exponential e to the st, the output will also be e to the st, but it will be scaled by its eigenvalue h of s, right? So by using that same concept, we are going to later in the lecture derive the Z transform equation. X of z is n equals negative infinity to infinity, x of n z raised to negative n. Plug in x of n, you will see that unit step will only be valid or 1 in this case between 0 and infinity. So we can adjust the limits on the summation here. We still have z raised to negative 1. Now we see that this is an infinite geometric series. So we can use the formula from before, but we will have to use it as long as the magnitude of z raised to negative 1 is less than 1, right? We had to make sure that, so this is going to be 1 divided by 1 minus r. In this case, r is z raised to negative 1. Or we can write it in this form as well. Usually what you will see is Z transforms being expressed using negative powers of Z. You will see that. But they can always be multiplied and divided by Z, in this case, to express as Z divided by Z minus 1. They are both equivalent, but you will see this negative powers of Z appear a lot more often. Now this converges as long as, so this is what is happening here. Let's see. This is being rewritten as z raised to negative 1 raised to n, right? So now when you put it in the formula, you will see that you need magnitude of z raised to negative 1 to be less than 1 in order for that to diverge. In other words, the magnitude of this complex number z should be greater than 1. That defines your region of convergence. So the region of convergence here is z such that the magnitude of z is greater than 1. That's going to be your region of convergence. Z is a complex number expressed in polar coordinate system as r e to the j omega. So now if I have a z plane here, this is my z plane, and I sketch the real part of z on the x-axis and imaginary part of z on the y-axis, I can have magnitude of z greater than 1 as everything that is outside of that unit circle. So think about this. When you had Laplace transform, what happened for u of t? When you did Laplace transform of u of t, we had what? 1 divided by s minus 1. Is that right? And our pole was at 1 in that case. 1 divided by s. Oh, 1 divided by s, sorry. let's see. So the pole was at 0, right? Let's see here. And because it was right-sided, u of t is right-sided, our region of convergence was to the right of the rightmost pole, right? Now, think of how do we go from here to here? What I do is I essentially imagine this j omega axis collapsing into a unit circle, essentially folding into a unit circle. When it folds into a unit circle, you exactly get this. And the region of convergence over here was to the right of the pole, and as it folds, you will have this region of convergence to the outside of the unit circle. So, you can just think of the j omega axis as a vertical axis collapsing top down here, bottom down up here, right? Collapsing into a unit circle. And for other transforms, it might collapse into some other circles of different radius, but it essentially collapses into a unit circle in this case. So when we had earlier for Laplace transform, the region of convergence outside of that through the right of the pole, over here it translated to outside of the unit circle. So later on you will see that there is a mapping between how the ROC happens in Laplace to ROC in the Z domain. So if it was a left-sided signal, it would be absolutely right. If it was a left-sided signal, it would have been inside of that unit circle or inside of a circle, right? So we'll see examples of both those cases in just a bit. But you're right, it would have been inside of the circle. So that's you would draw a circle, you have a 0 at 0, and you have a pole at z equals 1, and you would draw a circle, in this case a unit circle because the radius is 1, and everything outside of that circle, excluding the circle itself, would be the region of convergence. Next. What about, so from u of n, we are now going to a raised to n. A belongs to the set of complex numbers. What would be the z transform here? Again, a raised to n u of n is also a right-sided signal, and when we glance at the ROC here at the end, you will see that it is outside of a circle of radius absolute of a. But it is on the outside because the signal itself is a right-sided signal. Now, how do you find that out? Well, the process is similar, right? So x of z is summation of n equals negative infinity to infinity, x of n, z raised to minus n. Now, this can be, we are going to substitute x of n here. We get a raised to n. U of n is going to be 1 for time 0 to infinity. So we have included that, z raised to negative n. Now, all of this can be written as a times z raised to negative 1 raised to n. So that's going to be our r in the infinite geometric series formula. So that would converge to 1 divided by 1 minus r only when r itself, so in this case a z raised to negative 1, absolute of that is less than 1, right? Which essentially implies that magnitude of z is greater than magnitude of a. So we can write it as a inverse power of z, or we can multiply and divide by z and write it in this way, z divided by z minus a. So what we have is a 0 at 0, and we have, more importantly, we have a pole at a. Now, because a is complex, it could be here, it could be here, it could be here, it could be here, anywhere, right? It doesn't have to be real. If it were real, then it would lie on the horizontal axis, but it is complex right now. So what I'm considering is a is some complex number here with a negative real part and a positive imaginary part. So the magnitude of a would be the radius of this circle, and based on this divergence criteria, I know that magnitude of z should be greater than that, so outside of that circle with radius magnitude of a. So again, outside of that circle, because the signal itself is right-sided. So a raised to n u of n, the z transform is z divided by z minus a, and your pole zero plot and the region of convergence is shown over here, outside of the circle. Next, what about the z transform of a left-sided signal? In this case, you have negative u of -1 minus -n. And when you sketch this out using your time shifting and flipping properties, you will see that this turns out to be a left-sided signal. Apply the z transform equation. You have n equals -infinity to infinity, x of n z raised to -n. This is only valid between -1 and -infinity. It's a left-sided sequence when you sketch it out. The minus sign appears because of that minus sign over there. And once you write this as a sequence, you will see that that sequence turns out to be negative of z plus z squared plus z cubed and so on as an infinite series. That will converge only when magnitude of z is less than 1, and it will converge to that negative comes in because of this and because of that. But otherwise, it will be z divided by z 1 minus z. So what we did was factor out a z here so that we can use the sum of geometric series formula, and then we can write it in this form. Could you go back to the slide? Okay. I'll just give a second here. All right. So the z transform, it looks like z divided by z minus 1. And if I highlight this, I think I have seen this before. Z divided by z minus 1, I saw that right here for u of n. So it turns out that u of n had the same z transform as negative u of -1 minus -n. Same z transform. However, its region of convergence, based on the criteria that we obtained by the region of the converging properties of sum of geometric series, it will only converge when magnitude of z is less than 1, which means inside the unit circle but excluding the unit circle. So the two z transforms, they had the same function in z, but they were distinguished by their different regions of convergence. So it's the same as u of n, but has a different region of convergence. That was outside of the unit circle. This was inside of the unit circle. So again, that it is, when you look at it in terms of comparison, that would have been to the left of the j omega axis. When you fold that down, it will be to the inside of the unit circle. All right. Next, let us look at some properties. Some of these properties will appear very repetitive because you have seen them since Fourier series, again in Fourier transform, again in Laplace transform, and now again in Z. The things that I'm talking about are, because we have been observing linear time invariant systems, the linearity property will be there. The time invariant property or the time shifting properties will be there. The time convolution and multiplication in the Fourier domain or Laplace domain will exist, right? So those kind of properties will be there in all these transforms. So linearity, if there's a time sequence, discrete time signal x of x1 of n, whose z transform is given to us as cap x1 of z with a region of convergence as r1 in the z plane, and there is another signal x2 of n whose z transform is cap x2 of z with a different region of convergence r2, then the weighted sum of x1 and x2 will be the weighted sum of their individual z transforms. A and B are scalars in this case. ROC, the same way we found the ROC of Laplace transform is going to be the intersection of those two regions. Now, if I think about this, region of convergence for some of these guys is to the inside of a circle, and for this outside of a circle of radius absolute of a magnitude of a, over here outside of a unit circle. So, and I'm trying to find the intersection here. So one possibility is a ring, right? A ring where it is a region of convergence. So that's what we will see here in this particular, well, not in this example, but in a later example. So what we have here is x of n, a discrete time signal whose z transform is what we are after, right? Calculate the z transform of x of n, which is cosine omega naught n u of n. So by applying Euler's formula first, I'm going to break that cosine omega naught n into half e to the j omega naught n. So let me see here. This cosine is being broken down into half e to the j omega naught n and half e to the minus j omega naught n. U of n remains as is. Now from here, I can individually apply the formula of z transform. So let me quickly do that over here so that you guys see this in the work. So x of z is going to equal, because I have a u of n, I can directly start with n equals 0 to infinity. For u of n, I'm going to have a 1. For half e to the j omega naught n, I'm going to have half e to the j omega naught n. And I believe I will simply have z raised to negative n here. Plus, for the next guy, still 0 to infinity, still a 1, and half e to the negative j omega naught n and z raised to negative n, right? And now I can rewrite this so as to leverage the sum of infinite geometric series as this. I will say half e j omega naught z negative 1, all of that raised to n, plus and 0 infinity half e, let's see, in this case I need negative j omega naught z negative 1, all of that raised to n, right? And now I can focus on the region of convergence. So that is going to be my r, right? For the first one, at least r, magnitude of r should be less than 1. What does that imply? That implies that if you bring out the half, e j omega naught, let's see, oh, I can't do the half inside. Half should be here. Half is not being raised to n. Yes. So e to the j omega naught z negative 1, magnitude of that should be less than 1, right? So this will essentially give me the magnitude of e to the plus j omega naught, z raised to negative 1 will come on the other side. So that will converge, and if I include this for the negative part, I will have that particular statement. That will converge when magnitude of z is greater than magnitude of e to the plus or minus j omega naught, which is simply 1. So outside of the unit circle, essentially. But the z transform itself is 1 divided by 1 minus r. So half times 1 divided by 1 minus r, write that for individual these two terms, and then simplify to write it in this form. So again, we are going back to, can I use the sum of infinite geometric series to find what the value, convergent value is? And also, because magnitude of r should be less than 1 for it to converge, I can use that for individual term to find what that is. I would be looking at an intersection of these two regions. However, both of them are essentially telling me the same thing. Magnitude of z should be greater than 1. So the intersection will also be that same thing. So outside of the unit circle. Next, let us take a different time signal here, discrete time signal. 3 times 2 raised to n u of n minus 4 3 raised to n u of n. So for each of them, I'm going to write their z transforms using the general result that we derived earlier for a to the n u of n. A to the n u of n was z divided by z minus a. So in this case, 2 raised to n u of n would be z divided by z minus 2, where magnitude of z is greater than 2. So outside of the circle of radius 2. And for the other term, which is 3 raised to n u of n, you would get the z transform to be z divided by z minus 3, and the region of convergence is outside of the circle 3, right? So now if I find the intersection of these two regions, I know that they will only intersect when magnitude of z is greater than 3, right? So again, it goes back to the same relationship, the mapping between Laplace and z. Right of the rightmost pole and right of the rightmost pole, the intersection will be to the right, right? So in the same way, outside of circle 2, outside of radius 3, it will be outside of the outermost pole, right? Outermost pole here, which is at 3. So using linearity, because we still have these two things to include 3 and 4, we have 3 and 4 there, and then we have, using linearity, we have written down x of z, and then ROC was obtained by finding the intersection. So let's see if I can sketch this out here. One was a circle of radius 2 and one was a circle of radius 3, not a circle here, but right. And when you find the intersection of them, so one goes outside, right? So one is yellow, say, one is outside this, excluding the circle of radius 2, and then the other guy is outside that. So the intersection would be only outside the outer circle. So z greater than 3. Okay. Let's use a time shifting property. Very similar to time shifting properties in your previous transforms. If you have x of n whose z transform is x of z with a region of convergence R1, then when you shift x of n by some time n0, which could be a delay or it could be an advance, what will happen is in the z transform, in the z domain, you will multiply by z raised to negative n0. Your region of convergence is now R2, where R2 could be original region of convergence minus 0 when n0 is greater than 0. You see what would happen here. When n0 is greater than 0, you would essentially have z to the negative 1, z to the negative 2, z to the negative 3. So you have a negative power of z in that case, which means that I need to exclude 0 there. So when there is a delay, you need to exclude 0 from the original region of convergence R1. Or when n0 is less than 0, you would have z squared, z cubed, z positive power of z then in that case. So for that, your region of convergence would be R1 minus plus or minus infinity. So no major change in region of convergence, except that you might have to exclude a 0 or exclude a plus minus infinity. But in the z domain, you will have to multiply by z raised to negative n0, the amount of time shift. All right, next we have an example. X of n is 1 between 0 and 10. X of n is 0 otherwise. So this is essentially x of n is u of n minus u of n minus 11. So we have written the signal using step sequences. One is u of n, start it at 0, end it at 11, right? So that's what you will have over here. Start it at 0 and end it at 10. Now for each of them, I can write their z transform, and I can also write their region of convergence. For x of z here, I have, for u of n, the z transform is z divided by z minus 1. We proved that earlier. Because it's right-sided, your region of convergence is going to be outside of the circle, in this case a unit circle, minus, this is a shifted u of n. So it would be z divided by z minus 1, but multiplied by z raised to negative 11 using the time shifting property. So let us just highlight that. Because of this guy, you have this. And because of this and this, you have this and this. And in this case, your region of convergence is outside of the unit circle. So we are anyway excluding 0. So I don't need to explicitly write 0 again. It is going to be magnitude of z greater than 1. That is going to be your region of convergence. And then you can simplify this to write in this form, which is optional. But reaching here and finding the ROC is what is critical. No need to write minus 0 because it is already not there in this, right? Next. Now, how do you find the inverse z transform of a rational x of z? So what we have is a polynomial in the numerator and a polynomial in the denominator. So a lot of this is going to seem very similar to finding the inverse Laplace transform, but with one major difference. The difference is, instead of finding the partial fractions in the form of 1 divided by s minus a, we are going to want them to be of the form z divided by z minus a. Because the inverse z transform of z divided by z minus a is going to be a raised to n u of n, right? So the only difference here and here is we did not have an s in the numerator here. So we would want to save a z term in the numerator here, but all the other steps are exactly the same. Partial fractions, and then using the property of the signal. If it is right-sided or left-sided, then you would find the function and the region of convergence. So we'll talk more about those examples in just a minute. But the key difference I want to point out here is, in the Laplace transforms, when we are finding inverses, we wanted each term to be of this form, 1 divided by s minus a. There was no s in the numerator. But because we are trying to find z transforms, and our z transforms have a z in the numerator, because our property that the transform pair that we are using is a raised to n u of n. So the complex, the exponential, whether it is complex or not, the exponential signal will have the z transform as z divided by z minus a. Let's see. So based on the previous example, is it safe to say that time shifting doesn't alter the ROC? Yes, absolutely right. In that particular case, time shifting did not alter the ROC. It would have altered the ROC if you were playing around with things that are close to 0, right? So if you're close to 0, you go one way or the other, you might go from positive powers to negative powers of z, or vice versa. In that case, you might have an alteration in the ROC. But in this case, no, ROC did not get altered due to the time shift. Yes, you're right. Now coming back. So the summary of this slide is, save a z term in the numerator. Everything else will follow the same procedure as inverse Laplace transform. So x of z, I can write that as z squared. So it's the same rational z transform as shown in the previous slide. You have a polynomial in numerator and you have a polynomial in the denominator. Now, because I have a quadratic in the denominator, I can factor that out into z minus 1 and z minus half. The numerator, I'm going to split it up. I'm going to leave a z here, but I'm going to, so I'm saving this z here. Actually, save z term. So z squared, I'm writing that as z, and then one of the z can be inside, because now you have a linear function of z here and then a quadratic here. So a proper fraction. I can use partial fractions now. So z remains as is. Now inside the parentheses, I can break that into two partial fractions, k1 divided by z minus 1, k2 divided by z minus half. And if you use your partial fraction expansion, you will see k1 will come out to be 2, k2 will come out to be negative 1. So I can write now as z remains as is. For the first partial fraction term, I have 2 divided by z minus 1. For the second partial fraction term, I have negative 1 divided by z minus half. Now you see what happens. Because I saved that z term earlier, I can multiply throughout the two partial fraction terms to get 2z divided by z minus 1 minus z divided by z minus half, for which I know the x of n, for which I know the inverse z transform. X of n is going to be 2 because of 2, so linearity, that's the scaling. Z divided by z minus 1 is going to be 1 raised to n u of n, or simply u of n, minus a in this case is half, so half raised to n u of n. The only thing that we have mentioned, we have not mentioned here is, let's see, assuming x of n is causal. Right. So I'm assuming that x of n is a right-sided signal. Only then I can say that x of n is 2 u of n minus half u of n u of n as well. So for the examples that we are going to see in today's lecture, we are going to assume that our signal is a causal, so it's moving to the right. It's a right-sided sequence. So appropriately, we are going to find the inverse Laplace of each partial fraction term. I hope everything over here is kind of the same process as z transform, with the only change that you are saving a z term in the numerator. Next, another example over here. You have x of z as 1 divided by z multiplied by z minus 2 multiplied by z plus 1. What is the discrete time signal? The problem over here is there is no z term in the numerator to save. What do we do then? Well, we'll have to manipulate it, right? So the way we manipulate it is take one of these z's and put it as z minus 1 in the numerator, and then we multiply and divide by z raised to 1. Multiply and divide by, multiply by z raised to negative 1 and multiply by z raised to plus 1. Everything else is as is, right? So all of these are as is. Now that manipulation is going to help us save a z term in the numerator. So you see this, what happens is this z term can be saved. And I know that z raised to negative 2 looks like I can later use a time shifting property to write the inverse z transform for that. So I will leave that as is as well, right? But the time shifting property is ringing in my head here. Save z term in the numerator, right? Everything else is as is. So over here, what do we have? Here we have a proper fraction. I can use a partial fraction expansion here and then find k1, k2, plug it in there. What do you have? X of z is z squared remains as z raised to negative 2 remains as is. That z that we saved earlier can now multiply with each of the partial fraction terms. We have 1/3 z divided by z minus 2 minus 1/3 z divided by z plus 1. Now we need to find the inverse z of this first. Let's see. We are trying to find the inverse z transform of this first, and then apply the time shifting property. So the inverse Z transform of that would be, again, the assumption is x of n is a causal signal. It's moving to the right. With that assumption, I can write this as 1/3 2 raised to n u of n minus 1/3 negative 1 raised to n u of n. Now I need to still bring in the z to the negative 2. If you have z to the negative 2 in the z domain, that means that you had a shift of 2 in the time domain. So all the n's are going to become n minus 2. And that would be your discrete time signal. All right. Next, some more properties of Z transform. The time reversal property. If you have a time reversal, x of n becoming x of minus n, then the Z transform will go from x of z to x of z inverse. So essentially what you are going to do is all the z's in your Z transform, you are going to replace with z to the negative 1s to get the Z transform of a time flipped signal. And the region of convergence also gets inverted in this case. So r becomes r raised to negative 1. Let's take a look at the proof here. So the Z transform of x of n is n from negative infinity to infinity, x of n z raised to negative n. The Z transform of x of minus n, the flipped version, is going to be, I am essentially changing only this part to x of minus n because that's the new signal for which I need to find the Z transform. Z raised to negative n remains as is because of the formula of Z transform. Now apply a change of variable from m to negative n, which also implies that n is equal to negative m. Adjust the limits of the summation, x of m, z raised to m. I can write this as m from negative infinity to infinity, x of m, 1 over z to raised to negative m. So that is essentially x of 1 over z. So all my z's have become x 1 over z. That's it. So if you do a time flip, you invert the z to z raised to negative 1 in the z domain. Also your ROC gets inverted. So if it was outside of a unit circle, it will become inside of a unit circle and so on. Z raised to negative 1 might get confused with the z inverse Z transform. Are you referring to this guy? I'm not sure which okay, so over here z raised to negative might get confused with inverse Z transform. Oh, I see what you're saying. Okay, so inverse Z transform, I'm going to say like this, right? So that the inverse Z transform is an operator, so it would be apply on some other function of Z. Otherwise, you will just have this. So hopefully that resolves the confusion there. All right, so time reversal and that happens. All right, so using this, can I find out the the Z transform of a raised to negative n u of minus n? I know that a raised to n u of n is z divided by z minus a with ROC as magnitude of z greater than magnitude of a. Outside of the circle of radius, magnitude of a. We derived this earlier. Now, because all the n's have been moved to minus n, this is essentially a time reversal, straightforward time reversal. So x of z here should simply be x of 1 over z, right? What is that? I'm going to replace this with 1 over z, this with 1 over z, minus a is going to remain as is, and my ROC is going to be 1 over z greater than a. So this means this is going to simplify to 1 divided by 1 minus az, and ROC is magnitude of z is less than 1 over magnitude of a. Right. So that's how you are going to find, that's how we apply. What happened to the z to the negative 2? Where? There's no z to the negative 2 here. Oh, previous example. Oh, z, so that was for time shifting, right? So let's see, what color did I not use? Green. So that was for the time shifting. We saved it and then we applied the time shifting property to write it as n minus 2's. Okay. So, essentially, if you don't have a z term in the numerator, you'll have to force on it, right? And then when you force on it, you'll have to also compensate for it because you have forced it on that. And then that compensation will most likely reflect in a time shifting property usage at the end. All right, time shifting, time reversal, looked at an example, time differentiation in the z domain. So if you differentiate in the z domain, you multiply by n in the time domain. So because you differentiated in the z domain and you multiply by negative z, you multiply the time domain signal, the discrete time domain signal, by small n. Region of convergence doesn't change. Over here the example is, if you have a discrete signal n a to the n u of n, what is the z transform for that? The known z transform we are going to use is a raised to n u of n. The z transform is z divided by z minus a, with magnitude of z greater than magnitude of a. So a can be any complex number. So in that case, n a to the n u of n is simply the z transform is negative z, the first derivative of z divided by z minus a with respect to z, because all we did was multiply by n this particular signal for which we know the transform. So we essentially took this guy and we differentiated that with respect to z and multiplied it by a negative z. Our ROC not changing. And now you differentiate with respect to z, simplify to write your final result. The algebra, I will leave you guys, I will leave that to you guys to follow along. But we have essentially differentiated that function with respect to z once and then multiplied it by negative z. ROC did not change. Next, convolution property. Convolution in time should be multiplication in z, the same way as convolution in time was multiplication in Fourier transform, Fourier series, Fourier Laplace transform, everywhere else. Convolution in multiplication were transform pairs, and the same applies over here. Now recall that the discrete time LTI system has impulse response h of n. Then its output when the input is x of n is y of n can be found using the convolution sum, and the convolution is going to be between the impulse response and the new input or the arbitrary input signal x of n. It is commutative, so we can also write it as x of n convolved with h of n. And the convolution sum itself will be k equals negative infinity to infinity h of n minus k multiplied by x of k. Right? That was the convolution sum for discrete time convolution that we looked at earlier on in the course. Now, if x of n has a z transform defined as cap x of z, and h of n has the z transform defined as cap h of z, then output y of z in the z domain will be the multiplication of the z transform of the input as well as the impulse response. So x of z in this case is the input. Let's see. And this is essentially your transfer function, right? in Z, discrete transfer function. Now, one thing that I want to point out or stress on is this. I can write this h of z equals y of z divided by x of z. I can write that. But if you write this, I have seen this happen sometimes. Is this correct? That is a fatal error. So make sure that whenever you are working in time and z, s, or omega, you know where you can divide and where you cannot divide, right? So if you write things like this, I personally consider that as a fatal error, which means that that's a very, very severe error. Okay, let's move on here. Now, how do you prove this? Now, instead of actually proving this, I'm just laying out the steps for you to read. But if you carry out these steps, we have proved this kind of property in a similar manner, but I'm recapping some of the steps. Using the convolution sum to express y of n, like that, right? Start off with the convolution sum. Second, write y of z. Take the z transform of the result of the first step. Then apply a change of variable, m equals n minus k. Evaluate new summation results. Simplify. You will see that it will simplify into two summations. You will have to isolate them. One will be related to the input, one will be related to the impulse response. And that's how you would prove that property. But it is possible if you follow these steps along. There will be one summation because of the convolution. There will be another summation because of the z transform. But you'll have to separate them out into two summations. All right. How do we deal with repeated roots? So right now we have a x of z. I have a rational x of z. I have a z squared term in the numerator. I have a z minus a squared term in the denominator. So I've got two zeros at 0. I've got two poles at a. What is my x of n? Again, while doing this, I'm assuming that x of n is a causal signal. It's a right-sided signal. Let's see. Z squared divided by z minus a squared can be broken up into two terms. Z divided by z minus a multiplied by z divided by z minus a. The inverse z transform for each of them is a raised to n u of n. But because we are multiplying in the z domain, it would correspond to a convolution in the time domain, discrete time domain. So what we have is the self-convolution of a raised to n u of n, which using convolution sum can be written as k equals negative infinity to infinity a raised to n minus k u of n minus k multiplied by a raised to k u of k. Simply applying the convolution sum formula here. Now, because I have a u of n minus k, I can adjust the upper limit to n. And because I have u of k, I can adjust the lower limit to 0. And inside the summation, I will be left with a to the n minus k and a to the k, which essentially means I have a raised to n left over inside the summation. And more importantly, this is independent of k. So essentially, I'm adding a raised to n plus 1 times. So that would essentially mean this is small n plus 1 multiplied by a raised to n if n is greater than or equal to 0. If n is less than 0, then I have nothing in my summation and I would get a 0 sum otherwise. Now that I have written this out, x of n in bracket notation, x of n is n plus 1 a to the n if n is greater than or equal to 0. X of n is 0 otherwise, which means I can combine that to write this in in terms of unit step as n plus 1 a raised to n u of n. And I'm able to do this u of n because it is 0 otherwise, right? And it is only valid for n greater than or equal to 0. So repeated roots, try to write that as product of multiple z terms, and then find the inverse z transform by assuming that x of n is causal, then do a discrete time convolution. That's what we did over here. Next, this is probably the most important slide here today. How do I apply this z transform to discrete time LTI systems? What we are going to try to see here is, where does that z transform come from, right? So just as a reference, I'm going to also sketch an LTI system, continuous time LTI system here. And suppose we knew that the impulse response of the LTI system was h of t, and we were giving it input of e to the st, right? You remember, for LTI systems, what did we say? We said e raised to st are the eigenfunctions of continuous time linear time invariant systems. So in other words, when e to the st goes in, e to the st will come out, but it will be modified by h of s, the eigenvalue, right? And because we know how to do convolution, we can take this x of t, we can convolve it with h of t to write our y of t. And if you do this, you will see that y of t actually comes out to be e raised to st integration from negative infinity to infinity h of t e to the negative st dt, right? And this is why we said e raised to st is the eigenfunction, and it will be modified by h of s, our eigenvalue. And that's how we found out the Laplace transform. Laplace transform of a signal like h of t is h of s equals negative infinity to infinity h of t e to the negative st dt, right? That's essentially what we did. So this turns out will be the eigenfunction. This is the instead of that, I can say this is the eigenvalue. Now, what is the difference here? The difference is, for the continuous time signals, we had a complex exponential e to the st. What we have here for discrete time LTI system is z to the n. It is still a complex number, but the only difference is that it has a real and imaginary part, a discrete frequency here first. So when you compare this and this, what do you see? E to the sigma was the real part. Over here, r is the real part. And if you map the discrete conversation to the Laplace conversation, you will see that z raised to n is essentially the eigenfunction for discrete LTI systems, just the same way as e to the st was the eigenfunction for LTI systems. Now that's kind of the relationship between the two, and that's where your z transform definition comes from. Let's see, x of n, if that is the input, it goes into an LTI system with impulse response h of n, whose z transform is, say, h of z, cap h of z. The output can be obtained by either convolving the two discrete time sequences, x and h, or y of z can be obtained by multiplying x of z and h of z. Now consider, an input, a special input. Just the way we use this special signal e to the st, now we are considering a special signal for discrete time LTI system to be z to the n, right? That's our input, z to the n. How can I write the output? Well, if I start from this definition of time convolution, discrete time convolution, I can simply take h of n here and convolve it with z of n to write y of n. And because I know the convolution sum formula, I can write that as summation k equals negative infinity to infinity h of k z raised to n minus k. Now, z raised to n can be brought outside that summation because it is independent of k. So you get z raised to n. What you will have inside the summation is k equals negative infinity to infinity h of k z raised to negative k. And if you see this, the conversation that we just had with Laplace maps almost the same way to the conversation that we are having now for z. The difference is e to the st, which was the eigenfunction of continuous time LTI systems. Now we have z to the n being the eigenfunction to discrete time LTI systems. And h of z, which was our h of s, was the eigenvalue for Laplace. H of z is the eigenvalue for the discrete time LTI systems. And h of z is called the transfer function, just the same way as h of s was being called the transfer function for continuous time systems. Now, what would be h of z? It would be that. If you compare these two things, h of z is defined as k equals negative infinity to infinity, h of k z raised to negative k. That's where your definition of z transform comes from. That's where the formula comes from. Let us try to find out the output y of n when the input is r of n cosine n omega naught n omega naught u of n. And let us suppose that we know h of n, so we know the impulse response and the transfer function of the discrete LTI system. What is the output y of n? Well, first, because I see cosine signal, I'm going to exploit my Euler's identity to write cosine as half e to the j n omega naught plus half e to the minus j n omega naught. R of n remains as is, u of n remains as is. Now what I'm going to do is I'm going to isolate that into two separate inputs, half r e to the j omega naught raised to n u of n plus half r e to the negative j omega naught raised to n u of n. Now essentially earlier what did I have? Earlier I had the input as z raised to n, some complex number raised to n resulted in the same complex number raised to n with the transfer function evaluated at that same complex number, h of z. Using linearity, because I have two inputs here, half and half, scaled half and half, and I'm essentially treating z as r e to the plus j omega naught for this guy and minus j omega naught for this guy. All I would have to do to get the output is evaluate h of z with z being r e to the plus or minus j omega naught, but I would also have to multiply it, each eigenvalue, with its eigenfunction. What is that eigenfunction? Z to the n. So in this case, it would be r e to the plus j omega naught n for this guy and r e to the minus j omega naught for the second input. So by using the response of discrete LTI systems that we saw on the previous slide for the special input, we can write y of n as half r e to the j omega naught raised to n, transfer function evaluated at r e to the j omega naught plus half r e to the negative j omega naught n, which is essentially your z, right? So this is your z raised to n and another z raised to n. So we got z raised to n here and another z raised to n here. And because we have h of z at the end, the eigenvalue, we would need to evaluate h of z at that particular complex number, assuming that that is known. So that would be your response. Let's see. Conjugate property, a few more properties here. If you do a complex conjugate operation in the discrete time domain, then you need to first substitute z with z complex conjugate and also take the complex conjugate of the overall x of z function. ROC does not change. Time differentiation property, also called as the first difference property. It's called the first difference property because the time differentiation property is the difference of x of n minus x of n minus 1, the same signal delayed by one time unit. So what would be the z transform? If x of n z transform is x of z and ROC is r, then the first difference, the z transform is x of z for x of n minus z raised to negative n for the time shifting property and x of z for x of n, right? So essentially it is x of z multiplied by 1 minus z raised to negative 1. And in this case, because we have a z raised to negative 1, I'm going to have to find the intersection of r with absolute of z greater than 0 because of this. And this is r because that is r. All right, let's move on here. A few more properties being cited. Does the time differentiator apply to n0 greater than 0? So the first difference property is only for the first difference. So n0 is only equal to 1 here. This property is only for the first difference. But you can write this as n minus 2, n minus 3, n minus 4. Individually, what we would have to do is find the z transform of individual x of n and then use the time shifting property to write the other piece. All right, let's move on to accumulation property. If x of n has the z transform of x of z with ROC cap r, then what would happen if you accumulate all values of x from negative infinity to some stopping value or some stopping discrete time n? How much would you accumulate? The z transform of that would be 1 divided by 1 minus z inverse. That is coming from the geometric series, infinite geometric series that would add up multiplied by x of z. And in this case, the ROC would be at least original region of convergence intersection with, because of this guy, you would have this. And because of this, you would have that. Intersection with outside of the unit circle. Initial value theorem. If x of n is 0 for all time less than 0, then the first value, the initial value of x would be limit z tends to infinity x of z. This essentially comes from the definition of z transform. If you plug in n equals 0 there, you will see that it evaluates to that summation. Limit z tends to infinity x of z. That's your initial value theorem. All right. Now, in the next few minutes, I just want to address the topic of stability. All right. The way we had stability in the z plane, right? We want things to be on the left half plane. We don't want things to be in the right half plane. If there are things on the j omega axis, then it will lead to marginal stability. We can map all those things to the z plane as well. But instead of left and right of the j omega axis, we would have inside a unit circle and outside of the unit circle over here. So if we have the transfer function h of z, suppose we have a rational transfer function. So we have a polynomial in numerator, we have a polynomial in the denominator. Its poles, meaning the roots of the denominator, would define its stability. So suppose you have a signal x of n, u of n. It's a causal signal where a could be real, could be complex. The z transform of this is z divided by z minus a. Now, what would happen if a belongs to the set of real numbers? If a belongs to set of real numbers, this time signal would be purely exponential, right? Because it would have 2 raised to n u of n or 0.5 raised to n u of n. So it will be purely exponential, but depending on the value of a, actually I can write this, right? If a is less than 1, what would it be? It would be decay, right? Decay with increasing n. But if a is greater than 1, real but greater than 1, you would have a growing exponential. Grow with increasing n, right? But no matter what, for this case, it will be purely exponential. So take a look at this. When a raised to n u of n, when the magnitude of a is greater than 1, the limit of n tends to infinity absolute of a raised to n would be infinity. It would explode, right? It would grow. But if it is real, but if the magnitude of a is less than 1, in that case it will converge to 0. Stable behavior. Real less than 1 stable, real greater than 1 unstable, right? Those are some things that we have noted for this signal. Next, if a is complex, you would have what? Some complex number raised to n u of n. And because you have some complex number r e to the j omega, you can write e to the j omega using a cosine and a sine using Euler's, which means that it will have some oscillatory signal when a is complex. And the magnitude of a, if it is complex, so if it is purely complex, there is no r. If r is 1, the magnitude of a would be 1. Magnitude of a raised to n would also be 1 for all n. Now, let's take all of this and put it on a stability chart. What you have on the real axis is real part of z. What you have on the imaginary part is imaginary part of z. You see, when a was real, we were simply on the x-axis when a was real. But a could have been less than 1, a could have been greater than 1. When a was less than 1, we were inside this unit circle and things were stable exponential. But when a was greater than 1, we were outside of this circle but on the real axis, and we had unstable exponential behavior on our discrete time signal. Now, when a was complex, you see this, when a was complex, if we were inside the unit circle, considering that we have a causal signal, we would have oscillations but still stable oscillations inside. Magnitude of a less than 1. Complex but stable, right? So oscillations are there. But if magnitude of a is greater than 1, outside of this unit circle, over here in the quadrants, you would have unstable oscillations. That means that with time, the signal would go out of bounds. Right? So that's your unstable oscillation over there. So for oscillatory behavior, how would we know the frequency of oscillations? Well, suppose that a is a complex number with some magnitude a, and so the magnitude of a, e to the j angle of a. So a to the n can be written as magnitude of a raised to n e to the j theta a n. E to the j theta sub a n can be written using Euler's as a cosine and a sine, and we can see that both of these have a frequency of oscillation as theta sub a. So that would be the frequency of oscillation. But by looking at how these a value change in that z plane, whether they are on the real axis, whether they are outside the real axis, whether they are inside the unit circle, whether they are outside the unit circle, you can talk about their stability versus instability behavior, also talk about their purely exponential or oscillatory behavior. All right, so let me stop over here